First of all, I want to thank the organizers for this meeting and for giving me the opportunity to present these results. And it's great to be in Bangalore. So the title of my talk today is the Ricci flow analysis of financial assets. And this work was funded by the CNRS and the LPTMS. And I also wanted to mention, since it came up yesterday, that I happen to be a CEFIPRA alumna and first went to France on a CEFIPRA postdoc before I was hired by the CNRS. So Ricci flow. This slide here is a teaser, is a sort of teaser for the things I'm going to be speaking about today. And what you have here is data from NASDAQ represented in the form of a graph. So NASDAQ is a stock exchange, and the NASDAQ 100 is an index which is created for the top 100 companies on this exchange, excluding the financial companies. So on this graph, what I have as the nodes are the members of this NASDAQ 100 index. And we have data here which is computed for about 5 years. So starting from January 1st, 2020 till about 15th of November of this year, 2024. So this is daily data from Yahoo Finance. And all of the members of this index are the nodes, and the edges are stock correlations. So as you can see, this is a fully connected graph without any apparent structure. That is, all of the nodes are connected to, each of the nodes is connected to all the other nodes. And the average correlation on this graph is 38%. So why study stock correlations? Basically, you can think of the economy as being, you can think of the economy as being a complex dynamical system. And stock prices are actually a good proxy to study such a complex system. Also, the availability of very high quality data makes it attractive, makes it a good thing for scientists to try and study this. So as we saw in the previous slide, these correlations, this graph, the NASDAQ graph, for example, is highly correlated. And so therefore, you want to understand what might be the common factors that are driving the stock prices. The thing about an index like NASDAQ is that it divides all the available data into fundamental sectors based on the economy. And these fundamental sectors are rather limited. And there are 9 of them for the NASDAQ. And let me read out some of them. So you have 9 sectors: industrial, technology, retail, telecom, biotech, healthcare, transport, media, services. But that's limited, and it might not reflect the current reality of a company. For example, if you take GE started off as a utility company, and at some point it started a financial division. And at that point in time, at a certain point, the financial division began to represent half of the revenues of GE. So should you consider GE to be a utility company, or should you treat GE as a financial company? You can ask the same sort of question for Google. Should you treat Google as an internet company that runs a search engine, or is it an advertising agency? So this is where a data-driven analysis can be really useful in revealing factors that are driving stock prices. Also, stock correlations are at the absolute center of a lot of financial mathematics. So anybody who speaks about stocks is speaking about risk measure and risk modeling, and stock correlations are the beating heart of this sort of activity. A really important feature these days is to try and detect emerging thematic risk baskets. An example of this would be the Trump election, where there was a lot of talk about a green-brown divide. So should you, like green oil versus, green energies like solar or wind. So the question is, depending on the outcome of the election, your risk would be different depending on what your portfolio was exposed to. So stock correlations can help you detect such, and I hope to show you in the later slides how you can do things like this. Sovereign wealth funds and pension funds routinely use stock correlations to do portfolio allocation and portfolio optimization. And stock correlations are at the absolute heart of derivative pricing and options and everything. So, so this is a case for using for data-driven analysis. So the trend in data analysis these days is to borrow like very fancy methods from mathematics and to try and adapt them to studying discrete data and to study them on graphs. I'm going to skim over topological data analysis and go directly to geometrical data analysis. While topological data analysis can give you an idea of the system as a whole, geometric data analysis has the advantage of giving you local information. So geometric data analysis is centered around curvatures, and in particular the Ricci curvature. And the advantage of having looking at a quantity like this is that it's local. And when you have a local quantity that performs well all over the system, you're able to sort of draw global conclusions about it. You're able to draw conclusions about the geometry. You'll see how that works out. So there are many ways of doing the Ricci curvature, including a combinatorial curvature. But in the time that I have left, I'm just going to talk about the one that I've used for stock correlations, which is, in fact, because Foreman-Ricci combinatorial curvatures don't work very well for time series data. So it's better to work with Olivier-Ricci curvature and which is combined with optimal transport to give you, to look at your data. So Hamilton introduced the so-called Hamilton-Ricci flow. That was around 1982. And he introduced this flow equation in order to try and solve or respond to the Poincaré conjecture. I'm not going to go into the historical aspects of this, but a present-day statement of the Poincaré conjecture would be to try and classify three manifolds. So as we are all familiar with the classification of two manifolds, we feel it, and it's proved that you can think of like a two manifold, a surface can be positively curved, can have a positive curvature like a sphere, can be flat, or it can have a negative curvature like a saddle. So the question is, the simple question which was asked roughly 100 years ago is, could you do something like this for three manifolds? Can you take a very complicated looking three manifold and decompose it into a nice spherical part, a nice hyperbolic part, and a nice flat part? This involves a huge, this slide represents 100 years of heavy-duty mathematics and is still a very active field of research. So let me just say that Perelman solved this in 2003 onwards using ideas of the Hamilton-Ricci flow. And here you have a definition of the Ricci flow equation. So the Ricci flow equation, Hamilton defined the Ricci flow equation to look like the heat equation. So this is like a heat equation, except that it's written over the family of metrics in a parameter space of metrics. And his reason for doing this is that just as the heat equation gives you a sort of uniform temperature over your surface, he wanted to take the metrics and to use the curvature to smooth out the metrics and thereby see if he was able to, to try and see what happens to a surface or a manifold under the action of this. So on the right-hand side, you have the Ricci curvature tensor. So this is not the heat equation, it's highly nonlinear because this thing contains all the double derivatives of the metric of GIG. Also, this flow is prone to singularities, And they had to develop a whole technology called surgery to deal with these singularities. And you'll see a sort of a simpler version of this on graphs later. No, I'm going to skip this slide. So what I want to show you is just what does Ricci flow look like. So here I have a surface of revolution, and this is a surface. This surface was generated by Rubinstein and Sinclair. And now what we're going to do is you can see that it has paths with positive curvature, and you also see that it has paths with negative curvature. So let's see what Ricci flow looks like on this. So as you do the evolution of this space using this manifold using the Ricci, you see that the paths that the curve, this surface of revolution is already smoothing out, and the parts of negative curvature are expanding, and the parts of positive curvature are shrinking, and they're all coming together, and you find a sphere, which is the expected result in 2 dimensions. So this is the expected result in 2 dimensions. All of this was for continuous continuous nice Riemannian manifolds. So if we have an expectation to do this on discrete data, the big breakthrough for taking techniques such as these and applying them to discrete data came from the work of Jan Olivier. And Olivier's breakthrough was to be able to define a Ricci curvature for a metric space, not just for a parametric space of metrics. And the thing that Olivier considered was to take 2 infinitesimal balls in a unit metric space and to sort of move them along a geodesic, and to compare the distance of the centers and the distance between the balls. So that that involves the Wasserstein distance. So he was able to compare he took the ratio of the Wasserstein distance to the metric distance, and using this sort of coarse curvature, he was able to define this coarsening of the space. He was able to define a Olivier-Ricci curvature. This is very technical, but please bear with me. So just to give you an idea of what it looks like, you'd have the spherical surface, which has the kappa which is greater than 0, and then flat with kappa equal to 0, and negative with kappa less than 0. And the graphs, I'm anticipating myself a little. The graph would be a fully connected graph. This would be like a flat graph, and this would be a hyperbolic graph. Yeah, so I'm anticipating, I'm going to skip the graph. I'm going to ask you to believe me that this equation carries through for a graph. So we have kappa, the edge curvature of a graph is going to look like 1 minus the Wasserstein distance over dij. And I'd rather tell you how you do this for a toy model. So here we have a fully connected graph with 5 nodes and 10 edges. Yeah, 10 edges. So, so we are going to do like a toy optimal transport on this. So what I'm going to do is I'm going to take a mass, a unit mass, and I'm going to distribute it over I and all of its neighbors. So I'm going to put half of that unit mass on this site I and distribute the remaining 1/2 on all of its neighbors. Now I want to do optimal transport, so I want to shift the mass, this full distribution of M over I and its neighbors onto J. The nice part about dealing with a fully connected graph is that I and J have common neighbors. So all I need to do is to shift mass from I to J. So I have half on I and 1/8 on J. I want to get 1/8 on I and half on J. So that's quite a simple calculation. You do half minus 1/8, you get 3/8. And I say that the curvature, the Ricci curvature of this edge ij is then 1 minus 3/8, which is 5/8. So that's about 0.625. We have the Ricci curvature of this graph. So you can repeat this, this calculation for, if you do it for a graph of n nodes, you'll get like 1/2 of n over n minus 1, which is slightly larger than 1/2. Now we are, after all of this machinery, we are finally ready to define an algorithm to do Ricci flow on graphs. So this is following the work of Jost and his co-workers have done an enormous amount of work on this. This is work, and also his book is quite amazing on geometric analysis. And this is also work by Ni, Lin, Luo, and co-workers. So here, what we do is we calculate I'm simplifying, we calculate the Ricci curvature on an edge at time t and use it to define the distance at time t minus 1. So if you have a graph with positive curvature, you can see that when you propagate it in time, when you go from t to t plus 1, kappa greater than 0 reduces the edge weight and brings your two side points together. If kappa is equal to 0, you are not changing, you're just doing, they stay parallel. And sorry, if kappa is equal to 0, they stay parallel. And if kappa is less than 0, you're increasing your edge weight and your distance is going to diverge. It's going to increase and your 2 points are going to diverge. Oh my God. How much time do I have left? I'm going to skip this. You're going to believe me that you can do community detection. This is a benchmark. So you're able to do community detection. I won't even go into this because this is a case where the community is fixed and stocks, as we said, a case when communities are not at all fixed. So how do you cluster stocks using Ricci flow? So I have n stocks in my index. I have a price pi for a stock at time t. I'm going to define the return on this price. And the correlation between stocks I and j is Cij, not yet the correlation. Cij is the Pearson coefficient correlation defined in the standard way between these two, between the two stocks I and j. Now, using this Pearson correlation, I can define a distance between two stocks I and j, and I can use this distance to define a graph where the vertex of, where each vertex of this graph is a stock I, and the edge weights, and the distances are the edge weights. So stocks are positively correlated, and you have a fully connected graph, which would correspond to the spherical case, a difficult case. And how do you start to analyze this? Here we have data for this is a toy model. And this is a model which is, so stock correlations have been around for a very long time, but the econophysics community discovered them roughly in 1999 with Mantegna's work, and that continues to be the benchmark till today. And this is the 10 stocks toy model, which is Tuminello, Lillo, and Mantegna's work from 2008. So they picked up 10 stocks, and they built up the correlation matrix for it, and they used a minimal spanning tree to analyze this data. And so, sorry, I have to read this slide. So as you can see, these stocks are sort of clustered into 3 sectors. So I prefer to look at this. So this is the blue is the energy stocks. The red is the tech, if I remember right. The red is the tech, and the green are the energy stocks. See, this is why I have so many notes. I can tell you the names of this. So now we come to our toy model Ricci flow. We are going to do Ricci flow on this cluster. So you can see you can recognize some names. You have IBM, you have Motorola, and so on. I'll tell you the names as we go along. So the average correlation on this graph is 40%. So now what happens when we start to do Ricci flow on our model? Right, here you have the distribution of edge weights before you've done anything on the graph. And we calculate our starting histogram of Ricci curvatures. So you see that they're all spread all over the place. Though this is quite small, between 0.5 and 0.56. Now we flow this, we do 10 iterations of Ricci flow. And you see that the edge weights have completely split into 2 parts. We have edge weights around 2 and around 0, which are close together. And these are the links which are far apart. And likewise, we have a histogram of Ricci curvatures which go with it. So we say that these are very long links. So we can do surgery on this. We can cut them. And So when we look at our toy model and we do this, we see that our cluster has separated into two clusters. And here you have all the energy sectors which are completely split from the first cluster. So which is very pleasing to us because this is what we were looking for. And now we continue to look at the remaining 7 names, and we put it through Ricci flow. And again, we see that, I think that's 10 iterations. And we see that it's splits up again, and we have these longer edge weights, and we do surgery with them. And we see that it splits up into oil, and it splits up into tech. So we are quite happy to be able to recover the Mantegna's result on the toy model using Ricci flow, especially because doing a minimal spanning tree is quite unstable. It depends to a great extent on the initial conditions of your data. So if you add an extra day, if you take your correlations 1 extra day and calculate the matrix, you can get a different result, yeah, depending on your matrix. Also, we'll compare them in a bit. I have 3 minutes left to tell you all the main results of this work, which is the analysis of the NASDAQ 100 index, which is the same thing that you saw previously, fully connected with a correlation of 38%. So this is what the edge weights look like. And here we have the histogram of Ricci curvatures, and you see, yeah, I wanted to say that this normally, if you looked at 1/2 of n over n minus 1, this should be like slightly above 0.5, but because all the edge weights are not equal to 1, this is slightly less than 0.5, which is okay. So here we have our histogram. And now we are going to do Ricci flow. We are going to flow this, and we see that, oops, we see that nothing much happens at 5. Around 10 iterations, you see that the data starts to split, and we have a nice good split at 15 iterations on the NASDAQ 100. So here this is split into 2 groups of 34 and 66 stocks. So we want to look at let's look at the first. Let's look at the big cluster. Let's look at this doing a second level of Ricci flow on the big cluster of 66 stocks here. Right. So we are happy. We are pleased to see that this splits up into groups, and then we do surgery on the long links, and after 15 iterations, we have something that looks like this. And this is nice because at the second level of the NASDAQ, if you look, I'm really sorry, this slide is not very readable, but believe me that this is a level, this one is a bunch of semiconductor stocks. This is a bunch of semiconductor stocks. Now this is great, and it's interesting because the conspicuous absence in the semiconductor stock thing is that first of all, it's interesting because risk there's given the explosion of AI, and given the explosion of graphical using those graphical chips to do that, there's a huge amount of risk associated with being exposed to these stocks. So it's great to split out the semiconductor cluster, and what's most interesting is that NVIDIA is conspicuously absent from this semiconductor cluster. Everything, and NVIDIA is really the top performer if you look at the NASDAQ for this year. So that's interesting because we come back to thematic baskets. You will look at the next slide, and I'll tell you what we can say about this. So once again, we take the, what did I miss? Sorry. Okay, really sorry. Did I start late? No. Okay. So we took the thing, the other one, the big one, and then we did level 3 on it. And here, this is what we find. So this cluster that we looked at, this, you know, when I looked at it before last week, I said this is the worst performers. You can this is the worst performance of Nasdaq. So at least it contains some of the worst performers of Nasdaq. And on Friday, and I mean, when I landed in Bangalore and the news came out, it's actually that this is a piece of information that they wait for at the end of the year that happens. So Nasdaq has actually officially removed Moderna. Moderna is no longer a part of the Nasdaq index starting from last Friday. So this is good. So this is good because this index, and I apologize again, I didn't have time to make this slide properly. I'm going to tell you the names because this thing, this slide has it has the worst. It has Moderna, PDD, and MongoDB. These are amongst the 10 worst performers. And then it has also DoorDash and another stock which are amongst the 10 best performers. So we see here that we are able to capture extremes, we are able to capture the outliers by doing this analysis. So there are a number of points that I want to bring out in this. It's that, first of all, that Ricci flow is able to cluster an index like the Nasdaq, and it's able to produce meaningful data about it. The baskets, it's able to produce clusters which are like thematic baskets and which are going to allow you to calculate your risk associated with these. So each of these points, like finding the worst performers, being able to make a basket with the tech stocks, and the best performer, NVIDIA, being among the main market movers, all of these are very subtle and structured information about the stock market, which would be really difficult to have by any other means. Also, well, minimal spanning tree, which has been the main means that has been used for about 20 years in this field. So this is quite exciting. It's quite exciting. There's a lot of work to be done. There are a lot of future directions in this work. First of all, the Nasdaq is just one index. There are other indices. There are other companies. And most interesting thing that I'd like to do next is to try to be able to look at the curvature around the crashes. And I didn't have time to go into this, but the last point is that Ricci flow gives you the opportunity to be able to classify the links in your system. So it's a great way. A hyperbolic link is a weak link in any system, and it's a great way to expose fragility in your supply chains. The OT algorithm, this is a mine. It's of amazing things that can be done with it, and I hope to be able to do some of those things in the future. And thank you very much for giving me this. Thank you for your attention.
Questions?
So how do you calculate? You mentioned there was a distance called the
Wasserstein distance.
How is that calculated? How are D and W calculated from your data? I didn't understand.
In general, or from my data?
I mean, if somebody gives you a bunch of returns or something, I didn't understand how that's calculated.
So it's in the continuum, there's a very good, very properly defined way to do it.
Yeah, no.
So so the discretization of Olivier's discretization tells you how to do that. Yeah, Olivier's discretization tells you how to do that. So Olivier takes a metric space. He starts looking at geodesics on the metric space. He considers 2 points X and Y and considers infinitesimal spheres around them. And then he starts to flow those infinitesimal spheres along the geodesics. And then he asks, like, if the spheres are parallel, then the distance between the spheres and the distance between their centers stays constant. If your space is curved, then your geodesics are not parallel, and there will be overlap between your spheres as you move along. And that brings you straight, so the distance between your centers might be greater than or less than the distance between the spheres calculated along according to a weighted mean. So that brings you into the terrain of optimal transport and the Wasserstein distance.
I see.
So that's the key to, there are other discretizations possible, and Lott and Villani, I mean, famously got the Fields Medal for that. But this discretization is particularly is a good one to be able to put it on the graph. Because obviously you can discuss whether it's the right or wrong discretization forever and ever. But yeah. Kiran, I'm...
So thank you, Bhargavi, for this very nice talk. I know it's a very naive question because I know nothing about these kind of things. I imagine that people have many different means to do clusterings when they have data, probably using principal component analysis or things like that. So how does this technique compare with the usual ones? Is it more efficient? Are the results different? And things like that. And another question is, can you apply that to, I don't know, genetic trees or biology or I don't know, I mean, other things?
Yes, I mean, community detection is a huge field, community detection, and there are papers, there are review articles, the Newman review article, there's the Fortunato review article, and it's a huge field, and amongst the methods that are used are the ones that you applied. So the reason that well, first of all, this graph stock correlation is a bit special in the sense that this is a fully correlated spherical graph. So while the idea of Ricci flow is that you take a manifold and then you flow it and you separate it and your spherical parts will come together and your hyperbolic parts will fall apart, will separate. There are, I mean, this is a spherical manifold which is prone to have, you could have, the main work of Hamilton was to prove that the surgery, you can do surgery to control the instabilities of the spherical manifold. So I'm not in any position today to compare Ricci flow with all the techniques of community detection. And even community detection is one aspect of this. For me, the aspect which is really nice about Ricci flow is that you keep a local point of view, and you keep a local point of view at every part of your manifold. You have, and if you're doing a minimal spanning tree, you have to classify your links at the very beginning of your minimal spanning tree, and you have to cut things. And then you end up with situations where you have cycles in your graph and you have all sorts of things. Here you keep, for me, a major technical advantage is that you know that this is clean, that the main work done in proving the Perelman conjecture was to say that you can do this, that even though singularities develop, you can do surgery along the singularities and you're still clean. So any link that you're cutting, you're allowed to do that. And you're only cutting it at the end of your procedure. You're not starting by cutting links. So you're not messing with the topology of your system right at the beginning. That gives you a significant measure of stability while doing this. And yes, this has been applied to, people are getting excited about it and it has been applied, but stocks have not yet been done, and being fully positively correlated, it's nice to be able to do this with Ricci flow. So.
Okay, I had a very quick question. And actually, where do the stock prices actually go into computing, let's say, any of this, like the curvature? Or whatever?
Yeah, the stock prices go into calculating CIJ. You start with a matrix which is based on stock prices. Wait, I have to find that. Here.
So the correlation matrix
Is the stock.
that's the input, is it?
Yeah, yeah.
And that CIJ goes into constructing the curvature.
It goes into, yes.
Okay.
Yes. I mean, this gives you the first round of edge weights. And then with this round of edge weights, you calculate curvature and then you iterate. Yeah, but your starting point is this stock correlation, which is the return. It's the correlation of return. It's not the correlation of prices. It's the correlation of return.
Okay, so if there are no other questions, let's thank Bhargavi.
Okay.
Let's thank, I think this was the last talk, so let's thank all the speakers.
Thank you.